Um, the other set of problems that I saw most students struggle with involved the use of integration by substitution. So specifically, we had two problems. One was integrating 2x plus 2 over x squared plus 2x plus 2 dx, and the second one was integrating x times x squared plus 7 to the power of 5. So I have written them down side by side, and I will show you what substitution to do for both of them so that we get the hang of the process. So in the first one, we have, if you notice here, we have x squared plus 2x plus 2. If we, this is again, one rule was that look for the function with the higher order. Here, the power of 2 is an order greater than the exponent of x in the numerator, so we got to work with this. So if we let u equals x squared plus 2x plus 2, notice when we differentiate du dx, we will get 2x plus 2, which is actually what we have in the numerator over here. So this implies that du is 2x plus 2 times dx. Um, this is nothing but what we already have in the numerator in this problem. So this problem essentially reduces to, implies that a problem really is integrating 1 to 3, 1 over u, because this whole thing is u du. Um, so this is, I think, what a lot of students struggle with, is the recognition of the fact that this highlighted area is same as this, which is the numerator. And we will let the denominator be substituted by u. So our problem just becomes integral of u du, which when we integrate this, and I'm going to write down the limits, will just be log u 1 over 3, which implies our function is essentially x squared plus 2x plus 2, and then the log of that running from 1 to 3. So you would plug in 1 for x first, and then you would plug in 3 for x, and you will get the answer. In the second problem, this looks complicated, but notice that we have x squared plus 7, and then in the outside we just have an x and a dx. So again, the rule is that you let the higher order expression be substituted by u. So if we let u equals x squared plus 7, then du dx is 2x, implies du is x or 2x dx. So here, what we notice is that out of our 2x dx, we already have an x dx. What is missing is our 2. And we can insert 2 in here by multiplying and dividing our integrand by 2. So applying this trick, our integrand essentially becomes integral of 1 to 2, and I'm going to multiply and divide. So I'm going to insert 2 here, 2x x squared plus 7, 5 dx. And in class, we wrote this as 1 over 2, running from 1 to 2, x squared plus 7, 5. And I'm going to bring 2x dx here. Now we're in business. We see that the 2x dx is same as the 2x dx here, and this thing is same as u. So this expression essentially boils down to integrating 1 over 2 from 1 to 2 u to the power of 5 du, and its integration is essentially 1 over 2, and it will be u6 over 6, so I could actually write the 6 outside, u6 1 to 2, which is nothing but 1 over 2 or 1 over 12 x squared plus 7 running from 2 to 1, and we can plug in the values and get the answer. So the point to note here is that integration by substitution usually involves having a function in the integrand that is of a higher order than the function outside the integrand. So we have here x squared plus 7, and then we have an x dx. So recognizing that the derivative of x squared plus 7 is nothing but 2x, which gives us a part of what we already have here. In this problem, recognizing that x squared plus 2x plus 2, when differentiated, gives us 2x plus 2, which is essentially what the numerator is. So we can make that as a valid substitution. I hope that these two problems explain or make clear the logic and the rationale behind integration by substitution.